Hello students, so today we are going to do chapter number 1, exercise 1.1 from grade 10 maths. And we are going to do Euclid's division lemma in this video. Before starting with this, let's do a recap of how we used to do long division. Let's suppose if we have to divide 83 by 3 using log division, we'll do like this. 3 times 2 is 6, 2, bring down 3. 3 times 7 is 21 and remainder is 2. And if we have to verify if this calculation is correct or not, so we can say that 83 should be equal to 3 times 27 plus 2. Or we can say that dividend is equal to divisor times quotient plus remainder. So same approach is used in Euclid's division lemma. It says A is equal to B Q plus R, where A is the dividend, B is divisor, Q is quotient and R is remainder. And if you observe in this long division, this 2 is smaller than this remainder, 2 is smaller than divisor. So remainder is always smaller than divisor, that is B here, and is greater than or equal to 0. Now we will continue with the question. So we'll start with the question. Question number 1, first part. In this we have to find the HCF of 135 and 225 using Euclid's division lemma. So if you observe here, 225 is a bigger number than 135. So we will divide 225 by 135. We'll start with 1. It's 135. It's 0. It is 9. So we can represent the same thing using Euclid's division lemma, that 225 is equal to 135 times 1 plus 90. Now we'll continue our division. Now 90 is the divisor, this 135 is the dividend. So we'll do 90 times 1 is 90 and remainder is 45. So we can write it with the help of Euclid's division lemma, that 135 is equal to 90 times 1 plus 45. We'll continue our division. 45 is a divisor, now 90 is the dividend. 45 times 2 is 90 and 0 is the remainder. So we can say that 90 is equal to 45 times 2 plus 0. When 45 is a divisor, remainder is 0. So the HCF of given numbers is 45. Now we'll continue with the next question. In the second question, the second part of the first question, given numbers are 196 and 38,220. Here 38,220 is the bigger number, so we'll divide 38,220 by 196. We will start with 1. 196. It will be 6, it will be 8, it will be 1. Bring down 2. Then 196 times 9 is 1764. Subtract this. It will be 8, it will be 9. Bring down 0. So 19 times 5 is 900. 196 times 5 is 980. So remainder is 0. So with the help of Euclid's division lemma, we can say that 38,220 is equal to 196 times 195 plus 0. We'll continue with next question. So in the third part of first question, given numbers are 867 and 255. Since 867 is a bigger number, we'll divide 867 by 255. 255 times 3 is 765. It is 2, it is 0, it is 1. So with the help of Euclid's division lemma, we can say that 867 is equal to 255 times 3 plus 102. Now we'll continue division. 255 is the dividend now. 102 times 2 is 204. It is 1, it is 5. So we can say 255 is equal to 102 times 2 plus 51. We'll continue now. 102 is a dividend. 51 times 2 is 102. Remainder is 0. So we can say 102 is equal to 51 times 2 plus 0. So what is the HCF here? Yes, HCF is 51. Okay, so now we'll do question number 2. In question number 2, we have to show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5, where q is some integer. So here also we will be using Euclid's division lemma to prove this. So let's take a be any positive integer. A is any positive integer, and we will take b is 6. As you observe here, in place 6 is there, so we will take b is 6. So if b is 6, r should be less than 6, and it should be greater than or equal to 0. So it means we can say that r can either be 0, 1, 2, 3, 4 and 5. So case 1, when r is 0, so according to Euclid's division lemma, a will be equal to 6q plus 0. It means a is 6q. So what kind of number will be 6q? Will it be even or odd? Since we are multiplying q with an even number, so it will be an even number, because any integer multiplied with even integer will be even at the end. So this is even here. Now case 2, when r is 1, so a will be equal to 6q plus 1. 6q is even, 1 is odd, so even plus odd will always be an odd integer. So this will be the odd integer. So a is equal to 6q plus 1 will be odd. Let's name this equation 1. Now we'll take case 3. When r is 2, so a will be equal to 6q plus 2. This is even, this is even. Even plus even will be an even integer. So it means it will be an even integer. Now we will take case 4. When r is 3, a will be equal to 6q plus 3. This is even, this is odd. Even plus odd will be an odd. So this will be an odd integer. Let's name this as equation number 2. Now case 5. When r is equal to 4. So a will be equal to 6q plus 4. This is even, this is even, so it will be an even number. Now case 6. When r is 5, so a will be equal to 6q plus 5. This is even, this is odd, so a is equal to 6q plus 5 is an odd integer. Let's name this as equation 3. If you observe equation 1, 2 and 3, this and this, so any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5, hence it is proved. Now we will do question number 3. It says here, in an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So we have to find the same number of columns and the maximum number of columns. So it means we have to find HCF of both the number, that is 616 and 32. We have to find HCF of 616 and 32. So we will be using Euclid's division algorithm here to find the HCF. Since 616 is a bigger number, we will divide 616 by 32. So 32 times 1 is 32. Subtract this, it will be 9, it will be 2, bring down 6, and it will be 32 times 9 is 288. Subtract this, it will be 8. And so we can write this as 616 is equal to 32 times 19 plus 8. Now we will continue. 32 is the dividend now. So 8 times 4 is 32. Remainder is 0. So we can say that 32 is, let's change the color. 32 is equal to 8 times 4 plus 0. So here, as we observe that when 8 is a divisor, remainder is 0. So HCF of both the numbers is 8. So the maximum number of columns in which they can march is 8. Now we'll continue in question number 4. In question number 4, use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus, or for some integer m. Here again we will be using Euclid's division lemma. So let's say let a be any positive integer, and here we will take b is 3. As you observe here, 3 is there, so we will take b is 3, and so it implies that r, the remainder, should be less than 3 or is greater than or equal to 0. So it means here we have 3 cases. R can be 0, 1 or 2. So case 1, when R is 0, so A will be equal to B. B is 3 here. So we will write 3Q plus 0. Since we need to show the square of any positive integer, so we will square both the sides. It means a square will be equal to 9q square. We can write this as a square is equal to 3 times 3q square. As let's suppose this q square, 3q square, is equal to m, where m is any positive integer. So it means a square is equal to 3m. Now case 2, when r is 1, so a is equal to 3q plus 1. Again squaring both the sides, a square will be equal to 9q q square plus 6q plus 1. From the first two terms, we will take 3 as a common factor. So a square will be equal to 3q square plus 2q plus 1. Let's say this 3q square plus 2 is equal to m. So it means a square will be equal to 3m plus 1. Now, case 3, when r is equal to 2. So a will be equal to 3q plus 2. Again squaring both the sides, we will get a square will be equal to 9q square plus 12q plus 4. So we can say a square will be equal to 9q square plus 12q. We can write 4 as 3 plus 1. Right? So now from the first three terms, take out 3 as a common factor. So a square will be equal to 3 times 3q square plus 4q plus 1 and plus 1. So let's say this is equal to m, a positive integer. So it means a square is equal to 3m plus 1. If we observe from these three, we can say that square of any positive integer is of the form either 3m or 3m plus 1. Hence it is proved. Now in question number 5, use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9 plus m plus 8. So again we will be using Euclid's division lemma. Let's say a is any positive integer Here we will take b is 3. As you observe here, we have 9 here and we need to find the cube here. So we will take b is 3. So it means our remainder should be less than 3 and should be greater than or equal to 0. So we can say r can be 0, 1 or 2. So case 1. When r is 0. When r is 0, we can say that a will be equal to 3q plus 0. Since we need to find the cube here, so we will cube both the sides. It means a cube will be equal to 27q cube. We can say a cube is equal to 9 times 3q cube. Okay, so now we can say, let's suppose this 3q cube is equal to m, as here m is used. Yes, so it means where m is any positive integer, so it means we can say a cube is equal to 9m. Now we will take case 2. When r is 1. So a will be equal to 3q plus 1. We will cube both the sides. A cube will be equal to 3q plus 1 cube. Okay, here we will be using the formula of a plus b whole cube. Let me write down the formula. A plus b whole cube is equal to a cube plus b cube plus 3ab a plus b. Okay, now we'll continue here. So it means a cube will be equal to 27 cube plus 27 q square plus 9q plus 1. From the first three terms we can take out 9 as a common factor. So 3 it will be 3q cube plus 3q square plus q plus 1. Let's say this inside the bracket is equal to m, where m is any positive integer. So a cube will be equal to 9m plus 1. Okay, now we will do case 3. When r is 2. So it means a is equal to 3q plus 2, and cubing both the sides, a cube will be equal to 3q plus 2q. So we can say that a cube will be equal to 27q cube plus 8 plus 54q square plus 36q. Okay, from these three terms we can take out 9 as a common factor. So we can say that a cube, let's write it here, a cube is equal to 9 times 3q cube plus 6q square plus 4q plus 1. Let's say this inside the brackets is equal to m. This is equal to m. So we can say a cube is equal to 9m. Okay, here it is 8. This is 8. A cube will be equal to 9m plus 8. Hence, we can say that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Hope this video was helpful to you. Thank you.